Okay, so here is 1.5, which is atomic structure. Our outcome is I can represent the electron configuration of an element or ions of an element using the Aufbau principle. So in order to explore how we place electrons into their electron configuration, we're going to use a little metaphor here, which is going to be the boarding house. So in this boarding house, there are sunny rooms and there are pink rooms. Notice that on the first floor, there's no pink rooms, there's a kitchen instead. And we can see that as time progresses, that the boarding house gets filled up according to a set of rules. So looking at the boarding house diagram, match the symbol to its meaning. So this is going to correspond to a border. This is going to be a manager's code for B. And then C is showing me the bunk bed that boarders can sleep in. So looking at the manager's code here, we want to underline the floor numbers. So my floor numbers are 1, 2, 2, and 3. The types of rooms are in bold. That's going to be the S, S, P, and S. And then we need to highlight the number of electrons here. So there's 2 there, 2 there, 6 here, and 1 here. Okay. So considering what we have up here in our boarding house diagram, we want to try to figure out the rules that the manager uses to fill up rooms. So the boarding house will rent out beds on the blank floor first. So we can see that the first floor is going to get filled up before we start adding people to the second floor. So we're going to rent out the first floor beds first. Okay. Boarders are only allowed to double up in a bunk, so in a room. So we got to look here. Here, these two aren't doubled up, but once that the bottom bunk is filled, now we can double up. We see the same thing here, the bottom bunk, then the top bunk. So, boarders are only allowed to double up when all of those bottom bunks have been filled. The next floor will be open when blank on the floor below are occupied. So we see here that before we opened up this second floor, the first floor was filled. And here we're still adding people to the second floor, and we've completely filled up the second floor. Now we're starting to fill up the third floor. And you can see we go across and we continue to fill the third floor. So the next floor will be opened when all of the bunks on the floor below are occupied. The pink room on a floor will be opened up for boarders when, so let's take a look here. So before I put any electrons into any pink rooms here, or any boarders into any pink rooms, I should say, we see that the sunny room is filled up. So the pink room on a floor will be opened once all of the bunks in the sunny floor are occupied, on the sunny room. Okay, so that elaborate metaphor was just a way to kind of understand what the rules are for electron configuration and placement of electrons into an orbital fill diagram. So here we have a bunch of elements, and we're given our ground state orbital diagram and their electron configuration. So I've got hydrogen, carbon, oxygen, sodium, aluminum, and phosphorus. So what we want to do is examine these orbital diagrams and match the symbol with its meaning. So kind of very similar to what we were just doing. So what do we have that represents a single electron? So a single electron is going to be B. That is the one arrow pointing up. A pair of electrons with opposite spins, that's C. The next one that we have here is atomic orbital. We have sublevels and we have electron configuration. So the atomic orbital is going to be D. This is showing me a region of space where electrons are likely to be found. And in fact, it's showing me a p orbital to be specific. So that means that a single box is going to represent a sublevel. So we see that for example, for the atomic orbital p, that it's split up into px, py, pz. It's split into these three pieces. And then that means, of course, that E is our electron configuration. So what we want to do is try to apply those same rules from our boarding house example to explain and justify the fill order that we have here. So examine the orbital diagrams and electron configurations. Using the electron configurations, we want to underline the energy levels. So my energy levels are 1 and 2. We want to bold the sublevels. So my sublevels are S and P. Then we want to highlight the number of electrons. So this feels very similar to what we did with the borders. Okay. So the 2s and 2p sublevels are very close in energy, as are the 3s and 3p. Explain how the orbital diagram confirms that the 3s sublevel is lower than the 3p sublevel. So let's take a look, and that one asked about sodium. So how do I know that this 2s is lower in energy than the 2p? And I know that because the axis here along all of these is increasing energy. So because 2s is a little bit lower than 2p, we know that it's representing something with a little bit less energy. So we know that the 3s is lower than the 3p, or 2s is lower than 2p, because the s orbitals are lower than the p sublevels. Okay. So we know that because the S sublevels are lower than the P sublevels. Okay, so still moving on here. The lowest potential energy arrangement of electrons in an atom is called the ground state. The ground state electron configurations are predicted by a strict set of rules known as Aufbau principle. We also have Hund's rule, as well as our electron spin rule as well. So Aufbau comes from a German word which means building up. So we want to examine the diagrams and indicate which statements finish the sentence. So just like what we did with the boarding house example. So the lowest potential energy electron in an atom is going to be found at the 1s level. So those are the ones that are down here. They're the lowest in energy on my axis. Electrons will occupy a p orbital only after the previous s orbital is completely full. So this is kind of like when will the pink rooms be occupied? Only after the sunny rooms are full. Electrons can begin to occupy energy levels with the next highest integer destination, so 2 versus 1 or 3 versus 2, only after blank on the energy level below it are occupied. So before I put any electrons into my 3s here, I have to finish filling my 2p. So this is saying that before I move up to the next energy level, I need all of those orbitals to be full. The Pauli exclusion principle describes the restriction on the placement of electrons into the same orbital. So the Pauli exclusion principle can be expressed as if two electrons occupy the same orbital, they must have opposite spins. And the way that we illustrate that is by using arrows that go in opposite directions. So one arrow points up and another arrow points down. The reason they have opposite spins, if you have two electrons spinning in the same direction, there's going to be a lot of electron to electron repulsion. So by having opposite spins, that is actually the lower potential energy version of an atom. So electrons are deposited in opposite spins. Hund's rule. This is also sometimes called the good parent rule. And this says that electrons will only pair up in an orbital when all of the orbitals in the same sublevel have one electron. So what that means is that whenever I'm filling those p orbitals, I'm going to fill up, up, up before anybody gets a down arrow. So this is called the good parent rule because a good parent always makes sure that all of their kids get one helping before anybody gets seconds. So before anybody in a p orbital or a d orbital gets a second electron, each suborbital must get one electron. When single electrons occupy different orbitals of the same sublevel, they're going to have the same spin. So whenever we fill, we're going to fill spin up, spin up, spin up, and then we do spin down, spin down, spin down. So for each of the symbols below, let's describe how this is analogous to the boarding house model. So this is going to represent, with our arrow here, this is a single border, whereas this is going to represent a double border. So this is going to represent our sunny rooms, which is our s orbital, and this is going to represent our pink rooms. This is analogous to the manager's code. So what characteristic of electrons is not well represented by the boarding house model? It doesn't show the energy difference between S and P. So if we look at our orbital fill diagrams here, notice that 2s is a little bit lower than 2p, but whenever we look at our boarding house model, the sunny room and the pink room are on the same floor. So this boarding house model doesn't really represent that very well. So what could I do to change this model and maybe make it a little bit better, a little bit more accurate? We could have it like some kind of split level house where you come up onto the first floor, you go up a set of stairs to the second, and then to get from the sunny room to the pink rooms, you have to like go up a couple of steps, something like that. Okay, so in 11 here, we want to use all these rules that we've just discussed in order to fill out the electron configuration for sulfur and fluoride. Okay, so let's take a look at sulfur first. So I can write out my electron configuration for sulfur. Sulfur is going to be 1s2, 2s2, 2p6, 3s2, 3p4. Okay, so I'm going to place these according to our rules. So our first rule says that we need to fill up lower levels before we fill up upper levels. So I'm going to go ahead and put these 2 electrons here. Now I need to fill up my 2s before I can move on to 2p. So that's my 2s2 electrons. I've got 2p6 electrons next. So Hund's rule says that everybody gets one of the same spin before anybody gets a second one. And then now we have our 3s2 electrons. And then I've got 3p4. So I'm going to do 1, 2, 3, and 4. So there's my electron configuration written into my orbital fill diagram. Okay, so now let's go ahead and look at fluoride. So fluoride here is going to be a little bit different because it's not fluorine, it's fluoride, and it's got a charge. So normally the electron configuration for fluoride would be 1s2, or for fluorine rather, 2s2, 2p5. Now this is fluoride with a negative charge. So instead of this being 2p5, I'm going to add an electron to this valence shell, and we're going to make this 2p6. So now I'm going to go ahead and fill this in. So following my rules, I have to fill this level first. I have to fill S before I can fill P. 1 each before anybody gets 2. And this is my 6 2p electrons. So there's fluoride. Now let's look at a cation instead. So looking at sodium, the normal electron configuration for sodium is going to be 1s2, 2s2, 2p6, 3s1. Now this isn't regular sodium, it's the sodium cation, which means that it has lost an electron. So it's going to lose its valence electron, which is this 3s1 electron. So now I can go ahead and follow my fill rules and fill these in. So everybody's going to get 1 before anybody gets 2. There you go. And we notice that it's basically the same for fluoride and sodium, because this is how they both get to an octet, which is the most stable electron configuration. So now we have an excited state electron configuration. So this is any electron configuration that still has the correct number of electrons, but it has a higher total potential energy than the ground state configuration. So looking at number 12 here, how many electrons are there in an atom of X? We see that we have 10 electrons. So assuming that this is neutral, if we have 10 electrons, that means that we have 10 protons, which corresponds to neon. So is the arrangement of electrons in this diagram higher than the total potential energy in the ground state electron configuration? So we see here that this is an excited state configuration. And we know that because one of these 2p electrons, a 2p electron, has been promoted to the 3s energy level. So because this has been promoted up an energy level, this total amount of energy is higher than what it would be in the ground state. So the reflection question here is to summarize how these different rules help us fill the order of electrons. So Aufbau principle just means start at the bottom. It means you got to fill your lower energy levels before you can fill your higher energy levels. Hund's rule, also the good parent rule, that tells us that we fill in 1p electron before anybody gets a second electron. And the Pauli exclusion principle just tells us that they have opposite spins, and that tells you which way to draw those arrows.